Okay, so today we'll still continue with stoichiometry, but in terms of lab work, typically a lot of the stoichiometry that you do in the lab would deal with titrations. So titrations, you might be familiar with those with acid-base reactions, but you can do it with other types of reactions also. A little bit of vocabulary. So what exactly is a titration? It's a precise method to deliver volume of usually a known molarity solution to try to identify the unknown molarity of another solution. Equivalence point is when the moles of the two reactants are equivalent. They not necessarily equal because it may not be a 1-to-1 ratio between the two reactants. And then the end point is where you actually see a Keller change. So sometimes it's two clear substances making clear products. So you'd have to add some sort of indicator that will change Keller depending on what kind of reaction you're performing. And then sometimes you might actually have solutions that are already dyed a certain Keller because that's the type of chemical it is. So you wouldn't have to add an extra indicator for those. Another vocabulary term that's going to be very, very important is standardized solution. Sometimes you think you might have made a solution correctly, but out of your control, there are some conditions that apply that, again, are out of your control. And so we have to do something called standardized solution. And sodium hydroxide is kind of famous for this. So if you try to make a sodium hydroxide solution, maybe you are trying to make a 0.1 molar solution. Well, it turns out it'll actually be less than 0.1 molar, likely be less than 0.1 molar by the time you actually make the solution. And there's two reasons. Reason one and reason two. So first of all, sodium hydroxide will absorb water from the atmosphere. So what you think you're weighing at for solid sodium hydroxide may actually be sodium hydroxide and some water from the atmosphere. So and that's one respect of why you're going to have a lower molarity than you should, because remember, molarity is moles, in this case moles of sodium hydroxide divided by liters of solution. So you're actually going to have less moles of sodium hydroxide than you thought because some of it is actually water. And then the second reason is that after you've made your solution, the water itself is not pure water. Even though you thought it was pure water, water will absorb a little bit of carbon dioxide from the atmosphere and it will make carbonic acid. I'll write this full, okay? So then this acid will react with the sodium hydroxide that you just dumped in there. So a little bit of the sodium hydroxide will get neutralized by the carbonic acid that just happens to be in water. Even though you don't want it to be in there, it's still there. So your 0.1 molar that you thought you made is going to be less than 0.1 molar. How much less? I don't know. You're going to have to actually do a titration with a known material against the unknown, in quotations, unknown sodium hydroxide solution. Because we know approximately what it is, 0.1, but it's not going to be 0.1. So very good chance that this standardized solution idea with the two bullet points here for sodium hydroxide is going to be on the test. Okay, so what do we got here? We have a couple different questions, titration questions. So a student performs a titration with a monoprotic acid. That means something that has just one H, like an example would be HCl. Doesn't have to be HCl, but it very well could be. As opposed to this is a diprotic acid. And that's going to change how we would balance the chemical equation if we were trying to balance it. Okay, so we have a monoprotic acid. the student uses a standardized solution. So I don't know what they attempted to make initially, but after it was standardized, it was believed to be 0.110 molar. They have a burette, and of course here is the before and after that we're going to use, an appropriate indicator that's going to change colors so we can figure out the endpoint, which hopefully is very close to the equivalence point, and then any other laboratory equipment necessary. So it says, what should the student record as the volume of sodium hydroxide delivered? So volume final minus volume initial. You can think of this whatever way you want, but I think that would probably work for you. And we're looking for, let me go to a different color here. We're looking for the bottom of the meniscus where it meets whatever line. Now, whoops, that's not a very good representation there. Okay, so the actual line that I just drew actually has a little bit of depth there, so it kind of may impede what the actual spots are where that meniscus is going to meet the line. But I think this is going to be about 37.1, 2, 3, and it looks like it could be right on that line. With the graders and me, if I'm grading this, obviously there can be a little bit of a leeway depending on how well you can see where the actual increments are. And then the initial was 5.1, 2, 3, 4, 5, 6. So it's definitely 5.6, but it looks like it's a little bit more than 0.6, but not quite the 0.7. So I don't know, maybe like that. And let's go back and revisit this first measurement. I think you could probably get away with saying that that is directly right on that line. So we would have a 0 after that. So this is going to be important because 2 decimal places minus 2 decimal places give you an answer with 2 decimal places. Okay. So you just have to do that. 37.3 minus 5.65. You may have done that in your head, you may not have done it in your head, but we have something in the ballpark of that. Now again, I think there's probably a little leeway there because of your ability or inability to look and see exactly where those estimates are, where the bottom of the meniscus lies. Let me just rewrite that again. 31.65. Okay, so that was part A. I know we're already past this. Now part B, based on the information in your answer in part A. So this was my answer in part A. Determine the value of the concentration of the acid that should be recorded in the student lab report. So we're going to have to use answer A. Well, let me put it over here. 31.65 milliliters. And that is of the sodium hydroxide. And we had a molarity of the sodium hydroxide, which was 0.110 moles per liter or 1,000 milliliters. And that's for sodium hydroxide. And then it said it's a monoprotic. So monoprotic means H, we'll just call it X because we don't know what X is, plus sodium hydroxide. It's going to be a 1-to-1 ratio between those two things. So 1 mole of sodium hydroxide is equivalent to 1 mole of the acid. Again, I'm just calling it HX. And then we were told that we were given 25 milliliters of the acid. And I'm trying to turn that into liters because I want this to happen. Let's look at my units here that are canceling. the milliliters of base cancel, the moles of base cancel, and I'm going to be left with moles of acid divided by liters of solution. So that's going to give me molarity. So do all that math there, and let me write the answer. Okay, so that's the answer for part B. The part C, student accidentally adds more sodium hydroxide to the flask than was needed. So let's take a look where that would have impacted my math that I just did. Where is the volume of sodium hydroxide? It's this number right here. And it says that we added too much. Because this is on the top of that fraction, it's going to have a direct impact on our molarity answer. So this 0.139, if we would have added too much sodium hydroxide, would actually be an elevated number past 0.139. So I think I probably answered that question to the AP folks' satisfaction there. I think I have all the work here, so you can check that out on your own. I do want to note this. Sometimes it gives you multiple ways of doing the problem. I do not endorse you guys using the dilution equation, molarity times volume equals molarity times volume. The reason that it works in this case compared to factor label is because it's a 1-to-1 ratio between the two reactants, the acid and the base. But if one of the materials, the acid or the base, was in a 2-to-1 ratio or a 3-to-1 ratio, this number here is going to be off by a factor of whatever that coefficient change would be instead of a 1-to-1. So this can get you in trouble if you use it incorrectly. So I do not endorse that. I would rather you guys use the factor label method. Okay, second question. So now these are, this is still an acid-base question. There's a chemical called KHP. KHP has one H in it. By the way, it's called potassium hydrogen phthalate. No one likes to call it that. Everyone just calls it KHP. So KHP is a monoprotic, meaning that it's still the one, we'll call it X still. I know we actually know what the chemical is, but I'll just call it X. HX plus sodium hydroxide. So it's a 1-to-1 ratio between those two reactants. So we could get away with the M1V1 equals M2V2 kind of idea, but I would prefer if you guys would actually use factor label. So we have a number of things given to us. Molar mass is given to us. Grams of KHP is given to us. How much of the sodium hydroxide we needed to get a full neutralization. And with all that information, we should be able to figure out the molarity of the standardized sodium hydroxide solution. By the way, this is a very typical step one of doing a titration question. So you don't have to start where I started, but I am going to start with what I want in my answer. I need molarity, which is moles of NaOH divided by liters of solution. So I know that in 1 mole of sodium hydroxide, there is 1 mole of KHP. It's a 1-to-1 ratio because it's 1H there, monoprotic. Let's get the moles of KHP to cancel with the molar mass. Let's get the grams of KHP to cancel with the grams given. And then right now, everything cancels except for the moles of sodium hydroxide, which we'd like, but we also need the liters of solution. And it was told to us that it took 23.48 milliliters of solution. And we don't like milliliters because molarity is moles per liter. So I'm just going to change that to liters. And now we have all of our units. And that number is going to be that. Okay, now part two, I know it looks like a separate question, but it's really part two, is with our standardized solution. So we have a molarity, we have a volume and a molarity, and we're asked a volume. Because this is, is it a 1-to-1 ratio? It is not a 1-to-1 ratio this time. Sodium hydroxide, we're going to need 2 of these, and I'll show you in a second why. Here's sulfuric acid. There's 2 H's in sulfuric acid, so it's a diprotic. It's going to make 2 waters, and it's going to make sodium sulfate. Now you can see why I needed 2 sodium hydroxides. Without that, it wouldn't have balanced. So now, if you actually would try to use the M1V1 equals M2V2, your answer is going to be off by a factor of 2. So now, definitely the factor label is going to be a valuable item here. Let me move this up so I have just a little bit more room. Okay, so it says what volume. So I'm going to start off with volume of sodium hydroxide solution. And that corresponds with 0.1140 moles of sodium hydroxide. Now I got to get rid of moles of sodium hydroxide, and I just wrote a balanced chemical equation. So it's a 2-to-1 ratio, or a 1-to-2, whichever way you think about it. And then I have a molarity of sulfuric acid. And then I was told that I'm going to be using 20 milliliters of that sulfuric acid. So when you do that math, I think that comes out to be 85.9. It's going to round up to 86.0 milliliters. So factor label, factor label, factor label, factor label with stoichiometric questions. Okay, we don't know much about oxidation reduction. We don't have to know anything about oxidation reduction. It's still a factor label. We won't be able to use M1V1 equals M2V2 here either, because if you look at that balanced chemical equation, it's not a 1-to-1-to-1. It's a 5-to-1-to-8, and we have to see what we're going to be interested in here. So we have iron sulfate. Where is iron sulfate? There's iron sulfate. How do I know that? Because you need a +2 Fe to go with a -2 SO4. And then we have potassium permanganate, and there is our permanganate. Those are, so this is written ionically. So those are the 2 chemicals in question for this one. So we have a volume, we have another volume, we have a molarity. So volume, volume, molarity, and it asks probably for us to get a new molarity. Yep. Okay, so let's start. I always like to start again with what units I want in my answer. So 5 moles of Fe plus 2 is related to 1 mole of MnO4. Why am I using those 2? Because that's what I have information for. And then the molarity of potassium permanganate was given. That's supposed to be a dot there. So permanganate and potassium permanganate are going to have the same molarity because it's a 1-to-1 ratio. We were told how much we needed to titrate of the permanganate. And then to get it in concentration, we need moles per liter. And we were given 25 milliliters, which is 0.025 liters. So that's going to be all is going to be required to get that answer. Okay. And then you probably are unaware, why does this reaction not require an additional indicator? So I'm going to tell you. So we are dripping in, here's our burette. This has permanganate in it, or potassium permanganate, and that item is purple. So you drip some purple in, it gets neutralized. So down here, that turns clear. You put another drop of purple in, and it turns clear. You put another drop of purple in, it turns clear, until someone put in 16.42 milliliters. When they put that last drop to get 16.42 milliliters, it did not get neutralized, and it stayed purple. So purple will react because the permanganate's getting reacted, and it'll go away. It'll be clear. And then at some point, it will not get reacted because there's no more iron ions left. And then that next drop will make this purple down here. And when that happens, you stop, and that's how you know you didn't have to use any more material, and that's why we didn't need an indicator. Okay, very, 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 very similar question. We have a molarity. We have a molarity. Sorry. We have a molarity first, we have a volume second, and we have a molarity third. So this question is going to be about HI and potassium permanganate. We're using potassium permanganate again. So this also has a color change associated with it. So I think we've actually already answered the second part of the question. So many things have colors associated with them. Okay. So this one appears to be a 10:2 ratio between the two chemicals. So can't use M1V1 equals M2V2 on this either. So what volume is it being asked? So I'm going to start off with the molarity of the HI chemical. And then it's a 10:2 ratio. Oops. And then we have a molarity of potassium permanganate. And we have a volume. So I think all of our units are going to cancel except for this initial volume of the HI solution. And I think it's going to be a pretty big number here when you multiply and divide all that. And there you go. And that might be, yeah, that's it for titrations.